All right, welcome back, everybody. Today we're going to be doing section 6.6, which is where we get to learn the derivatives of the inverse trigonometric functions. The inverse trigonometric functions. Let me pull up the slides and we'll get started right away. Right, section 6.6. Here we go. So here's a bit of an overview, and I'll say some things as I go along here. But what I want to do first is review briefly those trigonometric identities that you need to memorize. So in the review lectures that I made, though in those lectures I talked about 6 trigonometric identities that you really do need to have memorized. And I'm not a big fan of memorization, but I just want to emphasize that yes, you do need to have those 6 memorized for your own edification, for the test. So please memorize them. We're going to look at them again here. Then we're going to do a little bit of review of inverse trigonometric functions, in particular the domains and ranges, the graphs, some important notes related to them, evaluating them, and then the end is where we'll talk about the derivatives of these functions. So we'll prove a couple of the derivatives of these functions and leave the rest to you to practice as an exercise. Then we'll look at some integral results, and then we'll have a summary of all of these derivative formulas at the very end. One thing I will say, though, is for this piece, let me mark this. Where is it? This piece right here. So I'm not going to dwell on this portion of the slides for too long, but if you do need if you do want a more robust review of inverse trig functions, you can actually see them on my YouTube channel because I already have my lectures for trigonometry recorded. So if you want a review of the inverse trigonometric functions, just look up that video on my YouTube channel and you can watch it there. Which section is it? I can't remember. It's Math 3. And I believe that the section is, oh man, I think it is 6.1. 6.1. I also have a review of just general inverse functions on that same playlist on my YouTube channel. So if you just need a review of what inverse functions are, it is also there. So there's lots of resources there. You could refresh your memory about inverse functions, the inverse trigonometric functions, and then you could come back and watch this to see the calculus part, derivatives of those functions. Up to you. It's there if you want to watch it. All right, so let's start with the trigonometric identities that you need to memorize. So just a refresher, these are the 6 that you need to memorize. The Pythagorean identity, the tangent identities, double angle formulas for both sine and cosine, and then power reducing formulas for both sine and cosine. So make sure you have these 6 memorized because you're going to use them nonstop in calculus. You're going to use them just all the time. The other double angle formulas for cosine can be helpful. There's actually 3 for cosine, and you can frankly just derive them from this if you don't remember them, but sometimes they do pop up. And then the other tangent identity is this one, but instead of it being tangent and secant, it's cotangent and cosecant. So sometimes that one can be handy as well if you're dealing with cotangents and cosecants. All right, so some review about the inverse trig functions. One, we got to talk about domains and ranges to begin. And this is a very important point when working with, frankly, inverse functions, period, but it's also important when working with inverse trigonometric functions. So remember that a function has to be one-to-one to be invertible. So you can't invert a function if it is not one-to-one. And outright, trigonometric functions are not one-to-one. If you think about one-to-one, essentially means it passes the horizontal line test. So if your function, the graph of your function, does not pass the horizontal line test, it's not invertible. That's really just what it is. So outright, if you think about the trigonometric functions, they're not invertible. Think about the sine function, right? There we go. That definitely does not pass the horizontal line test. So outright, these functions are not invertible. So if you remember, when you learned about these functions, you should have spent a decent amount of time talking about how you were going to restrict the domains of these functions, restrict the domain of these functions so that the result is invertible. Okay, we're going to review it right now, but that's what you have to do in order to even define the inverse trig functions. And just in general, You have to be very, very careful when you're working with inverse functions. You have to give careful consideration to the domains and ranges. This is one of the reasons why in my pre-calculus course, I really harp on my students and emphasize what is going in and what is coming out, inputs and outputs. What is the input? What is the output? Because when you get to inverse functions, everything is switched, and you have to be comfortable making that switch. So here's how we restrict the domain for the trigonometric functions in order to make them invertible. So for the sine function, we restrict the domain of the sine function. Ooh, actually, this should be, there's a slight typo here. These should be x's, 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 x, x. There you go. I'll fix that after the recording, but those should all be x's. So what are we restricting sine to? We are restricting sine to negative pi over 2 to pi over 2. So this set of angles right here. So what we're going to do is basically pretend that sine is only defined on this interval from negative pi over 2 to pi over 2. We're going to restrict the domain. Remember, the domain of these functions, sine and cosine at least, is all real numbers. The sine and cosine functions can handle any real number, any angle, any real number. But if you do that, then you don't have an invertible function. So we're going to specifically restrict the domain to be negative pi over 2 to pi over 2. And then for cosine, we're going to restrict the domain to be from 0 to pi. So pretend that cosine is only defined on that interval. And then for tangent, we're going to do something similar to what we did for sine. We're going to restrict the interval to be from negative pi over 2 to pi over 2, but excluding the endpoints. And that makes sense because a tangent is not defined at negative pi over 2 or pi over 2, because then you would have a vertical line, and vertical lines have undefined slope. So tangent, which is the slope of that line, could not be defined. So tangent is not defined at those endpoints. Okay, so these are the restrictions. We are restricting the functions as so. And the good news is this is one of the reasons that performing this restriction isn't necessarily a bad thing. The range is still negative 1 to 1 for both sine and cosine. And the range is still negative infinity to positive infinity for tangent. So even though we restricted the domain of these functions, we are still hitting all of the possible outputs that these functions could spit out, right? Sine spits out results that are between negative 1 and 1. And so even with this restriction, we can still get all the possible outputs between negative 1 and 1, which is great. Same thing for cosine, same thing for tangent. So it's not so bad to perform this restriction. We just got to remember that we did it, we actually did this. Now, since inverse functions invert the domain and the range, we have this. Arc sine has a domain of negative 1 to 1 and a range of negative pi over 2 to pi over 2 inclusive. Arc cosine has a domain from negative 1 to 1 and a range from 0 to pi. And arctangent has a domain negative infinity to positive infinity and a range negative pi over 2 to pi over 2. Inverse functions switch the domain and the range. That's essentially what's happening, right? Here are some graphs. Here's what the graphs look like. So this is the sine function restricted to this interval. There you go, just restricted to that interval. Notice pi over 2 and negative pi over 2 are included. And then this is the graph of arc sine or inverse sine. And if you remember when you learned about inverse functions, we're just reflecting this graph across the line, y equals x. That's how we're getting all of these, like so. So reflect this across this line and you get the inverse. There we go. That's what it is for sine. This is what it looks like for cosine. So here is cosine restricted to the interval 0 to pi, inclusive, I should say. And then if we want to graph inverse cosine, we reflect it across the diagonal, and we get this. So you notice again that when we draw these inverses, now the domain is negative 1 to 1, and the range is 0 to pi. And then here's what it looks like for tangent. So here is the tangent function between negative pi over 2 and pi over 2, and then this is the arctangent function. Notice it's defined for all real numbers. But here's the thing, and I'm going to emphasize this now, and you will hear me say it a lot. We really, really like We really, really like the arctangent function because it is bounded. It's a bounded function that is defined on all real numbers. That's just a beautiful property to have. Beautiful property to have. And we're going to see it a lot later on in the course when we get to sequences and series, okay? So this is a graph of a function that you want to have memorized. You want to be comfortable with arctangent, and we just love arctangent. The three functions that we love are sine, cosine, and arctangent because they are bounded. They're defined everywhere and they're bounded, which is amazing. Okay, so some important notes. Something you might have known, or I'm sorry, something you might not have known, or maybe nobody has told you. These functions are called arc functions because the output of these functions is an angle given in radians. So this is one thing to keep in mind. The outputs of these inverse trig functions are angles. They're angles. And because they're given in radians, what they're really doing is they're giving you the arc length. They're giving you an arc length. This is one of the reasons radians are so nice because they correspond to arc lengths. So the output of these inverse trig functions are arc lengths. And that's why they're called arc sine and arc cosine and arc tangent, because that's what they're telling you. They're saying, hey, if you put in this result, it will tell you the arc length. That's what it is. Now, here's my suggestion. Whenever you're trying to evaluate or inverse trig functions, the best method for understanding them is to say this sentence out loud to yourself. I highly recommend it. I highly recommend you practice it. But when you're working with something like arc sine, what you're really saying is what angle has a sine of blank. All right, let's try one just to kind of refresh your memory. Try to do this one on your own and then we'll talk about it. So, what is inverse sine of -1/2? What do you think? All right, got to say something out loud. Take a stab at it, take a guess. You can say it to yourself, to your friend, to your sister, to your dog, whoever. All right, now try to work it out yourself and see if you can compute the inverse sine of -1/2. Oh, there you go. Okay. Now let's do it together. And I'll explain how I do these types of things. When you see an expression like this, the way that you interpret it is this. You say to yourself, this thing is the angle whose sine is -1/2. So what is an angle that has a sine value of -1/2? Think about that for just a minute. What is an angle that has a sine value of -1/2? Ponder it for a sec. All right. Now there is one catch here. One catch. I was saying what is an angle that has a sine value of -1/2, but remember there are infinitely many angles that have a sine value of -1/2. But that is precisely why we restricted the domains of those trig functions, so that way we could make this result unique, so that we could actually define an inverse. So this expression here is saying what angle in this interval has a sine value of -1/2. So in other words, we're going to answer this question. Sine of theta equals -1/2. What could it be? Well, since sine is vertical displacement of a point, we just need to imagine the unit circle. So here we go. Here's the unit circle. Oops. Here's the unit circle. We are restricting ourselves to this region right here because this is how we restricted the sine function. So what angle in that interval has a sine value of -1/2? Okay, it's got to be this right here, right? Short leg, long leg. So this implies that that's going to be -1/2, and this is going to be √3/2. So what is this angle right here? This angle? The angle is -π/6. So the sine, the angle that has a sine value of -1/2 is -π/6. So that means that arc sine of -1/2 is -π/6. Ta-da! That's how it works. That's how it works. So again, This, this is the phrase that's going to save you when you do these things. Okay, there we go. We did that one. Okay, now let's try to do this one. So this one's a little bit trickier, but think about how you would do it, and then we'll do it together. How would you start it? All right, now say something out loud. How would you start this? Okay, now try to work it out on your own, and I'll give you a little hint here. Think about SOHCAHTOA and see if SOHCAHTOA can help you figure anything out. All right, now let's do it together. So what we're trying to do is this. We're trying to evaluate the sine of arctangent of 1/2. And I would say the first thing you got to realize is that arctangent of 1/2, that's an angle. So we're trying to compute sine of an angle. But what angle are we trying to find the sine value of? We're trying to find the sine value of the angle whose tangent is 1/2. That's what this means. Arctangent of 1/2 is the angle whose tangent is 1/2. Once we find that angle, then we can compute the sine of that angle. So let's start with the inside here. Here we go. Just a repeat. Yeah, so arctangent of 1/2 is the angle theta whose tangent is 1/2. And we want to know the sine of that angle. Well, remember that tangent is opposite over adjacent. That's SOHCAHTOA, right? SOHCAHTOA. Right, SOHCAHTOA. So since we know that tangent is opposite over adjacent, we know that the tangent of theta is 1 over 2. So what we can do is we can construct a right triangle where the height, or the opposite leg, is 1, and the adjacent leg is 2, and then this is the angle of interest. This is the angle that we want to take the sine value of. So if we want to take sine of this angle, we need to know the hypotenuse. Because what is sine, right? Sine is opposite over hypotenuse. So if we know the value of c here, well, we can figure out the value of sine. So here we go. We're going to use the Pythagorean theorem. The Pythagorean theorem yields that c is equal to root 5, so we can complete our triangle like so, root 5. And then now we can use, again, the right triangle definition of sine to say that sine of theta is opposite over hypotenuse, so we get 1 over root 5. That's the sine value. Ta-da! And you can stop right there. You can stop right there. You don't need to rationalize this. I don't care if you rationalize it or not. It's totally acceptable to leave it as 1 over the square root of 5. One additional note I will make is you do want to be comfortable with this process of constructing that right triangle and completing the right triangle and then using that right triangle to compute another value, because we are going to need that again when we get into chapter 7. When we do trigonometric integrals and trigonometric substitution, you're going to do this technique a lot. So if you want, you might want to rewind the lecture and rewatch this example, or just take some extra time to make sense of what we just did here, because we will do it a lot in the future. All right. Okay, next example. What is this limit? Okay, so ponder this one on your own and we'll do it together. What is the limit as x approaches 2 from the right of arctangent of 1 over x minus 2? Oops, let me do this first. There you go. Think about it for a minute. Okay, now say something out loud. What do you want to try first? All right, now go for it. See if you can work it out on your own, and we'll do it together in a moment. All right. Oh, say something else out loud, I guess. There you go. Okay, now let's do it together. Let's see. Well, one thing I know is that as x approaches 2 from the right, this value is going to get very, very large, right? So if x is getting really close to 2, then x minus 2 is getting really, really close to 0. So x minus 2 is getting very small, very, very small. So if the denominator here is getting very, very small, that means the whole fraction is getting very, very big, very, very big. So this input, 1 over x minus 2, is becoming gigantic as x goes to 2. So what is arctangent of larger and larger numbers? Well, it approaches something. What does arctangent approach as its input goes to infinity? Hmm. Hmm. Think about the graph, and we'll do the algebra right here. So if you remember the graph, it looks like this, right? Pi over 2, negative pi over 2. That's the graph of arctangent. So as x approaches 2 from the right, arctangent of this angle, whatever that, I'm sorry, arctangent of that value is going to approach pi over 2. And indeed, that's what happens right here. Now, what I wanted to do here is emphasize a technique that I'm using here. There's a limiting technique that I'm using. So um, it isn't immediately obvious if you did not study this specifically back in Calc 1, but what we can do is we can make a substitution. We can substitute the argument of the arctangent function with t. So we're going to call t 1 over x minus 2. And what happens then is that as x approaches 2 from the right, t approaches infinity, positive infinity. So we can rewrite this limit, the limit as x approaches 2 from the right, as the limit as t goes to infinity of arctangent of t. And now we can clearly see that the answer is going to be pi over 2. That's the limit as t goes to infinity of arctangent. Nice. All right. So all these minutes in, and we haven't done any calculus yet. We did a bunch of trigonometry, we did some review. Now let's get the actual calculus part. So here is the first result that's calculus related. The derivative of the arcsine function is 1 over the square root of 1 minus x squared. And we're going to prove this one right now. So we're going to prove that this is indeed the derivative of arcsine. Here we go. So first we're going to let y be equal to arcsine of x. And the reason we do that is because we're dealing with inverse functions, so it helps to label them so we can move between inputs and outputs in a natural way. So since we've written y equals arcsine of x, that means that sine of y is equal to x by the definition of an inverse function. And we also know that y is between negative pi over 2 and pi over 2 inclusive. And again, why do we know this? Specifically because we restricted the sine function to even be able to talk about an inverse sine function. So we know that whatever y is, it's got to be between negative pi over 2 and pi over 2 inclusive. And now we're going to use a good old technique from Calc 1. We're going to use implicit differentiation. So we're going to differentiate sine of y with respect to x. And we're going to differentiate the other side of this equation with respect to x. And now remember, when you use implicit differentiation, you've got to use the chain rule. So when we differentiate sine of y with respect to x, we get the derivative of sine with y left alone times the derivative of y, dy dx. Over here, this simply becomes 1 because the derivative of x with respect to x is 1. And now we can solve for the derivative dy dx, and we get that. So the derivative, dy dx, the derivative of arcsine x is equal to 1 over cosine y. But we're not done yet. We're not done yet because we started with x's and we need to end with x's. So we need to find a way to express cosine of y in terms of x instead. All right, here we go. Pythagorean theorem. So the Pythagorean theorem, or the Pythagorean identity, says that cosine squared y plus sine squared y has to equal 1. So if we solve it for cosine of y, we get this. Square root of 1 minus sine squared y, but remember, sine of y is equal to x, right? Sine of y is equal to x, right back here. Sine of y is equal to x. So that's where we get 1 minus x squared. Thus, the derivative of arcsine of x is equal to 1 over the square root of 1 minus x squared for all x between negative 1 and 1 inclusive. All right, there we go. So that's how we do this proof. You might have seen some similar proofs in Calc 1. I know there's at one point, actually, when you learn about implicit differentiation, you can actually prove what is it called? The inverse function theorem way back in Calc 1 if you make an additional assumption on the functions. So it's not too far off. There's one other note that I wanted to make, which is this. When we took a square root over here, And there's a subtlety here because anytime you take a square root, take this to heart, anytime you introduce a square root into your calculations, you must include a plus minus. You must include a plus minus. So if you were ever wondering when you're supposed to and when you're not, the answer is when you introduce it, you must include a plus minus every single time. And then maybe down the line, you'll be able to eliminate one of the cases. And that is exactly what happened here. So technically, when I solved for cosine of y, I should have said this, plus or minus square root 1 minus sine squared y. But I was able to eliminate the negative case specifically because cosine of y is greater than 0 on this interval, greater than or equal to 0. So we don't need the negative result. Let me draw a picture. Let me draw a picture. Remember, here's the unit circle, but we restricted ourselves to this interval in order to talk about arcsine, right? Well, on this interval from negative pi over 2 to pi over 2, cosine is positive. So we're going to pick the positive result, not the negative result. And so that's why we eliminated that case. All right, so a little side note there. Long story short, the derivative of inverse sine is 1 over square root of 1 minus x squared. Okay, now let's use it. Let's use it. So let f of x be arcsine of x squared minus 1. Find the domain of f, first of all. So find the domain of this function. Find the derivative of this function. And then find the domain of the derivative. So this one I want you to try on your own. So think about it for a minute. First, just ponder it. All right, now say something out loud about how you would begin. What would you do first to say, find the domain of f? How would you do that? All right, now try to work it out on your own. Try to find the domain of f, and then once you do, try to compute f prime of x using the formula that we just proved in the previous slides. All right, now let's do it together. So how do we find the domain of f? Well, first of all, what is the domain of sine inverse? Maybe I should say this first. What's the domain of sine inverse? Well, the domain of sine inverse is negative 1 to 1 inclusive, because that is the range of the sine function. So the domain of its inverse is the range. So it's negative 1 to 1. So what we need is we need this thing, x squared minus 1, to be between negative 1 and 1. So we get this. The input of the arcsine function has to be between negative 1 and 1. And this is the input right there. Now we can add 1 to all sides. So we get this inequality. And then when we take the square root, we're going to get this. Absolute value of x is less than or equal to square root of 2. Here's actually a perfect example of what I was just mentioning before. Why did we get absolute value of x here? Well, there's a couple reasons. One, the square root of x squared is equal to absolute value of x. That's right. And also, like I just said, whenever you introduce a square root, you must include a plus minus. You must include a plus minus. And that's exactly what this does, because the square root of x, the square root of x is x if x is positive, or negative x if x is negative. Something to ponder. We can talk about it more later, but same thing happening again right here. Okay, so what we need is we need absolute value of x. Oops. We need absolute value of x to be less than or equal to square root of 2. So that means that the domain of our function is negative root 2 to root 2 inclusive. That's the domain. Now, to compute the derivative, we're going to have to use the chain rule. So here we go. The derivative of arcsine is 1 over the square root of 1 minus that squared with the inside left alone, right? Inside left alone times the derivative of the inside, which is 2x. There we go. Now, when we simplify a little bit, we get this. So FOIL everything out from that binomial, you'll get that. We can simplify a little bit, and now we can actually factor out an x squared from both of those terms. And when we factor out the x squared and then pull it through the radical, we get absolute value of x. Once again, because square root of x squared is absolute value of x. Yeah, it's not just x, it's the absolute value of x, because whenever you square something, it always makes it positive. All right, now what's the next? Oh, we're not done yet. So we found the domain of f, we found the derivative. Now we got to find the domain of f prime. So we got to find the domain of this function instead. Let's do that over here. First thing, when we look at the denominator of our derivative, this thing right here, right away we can see that x cannot be 0. If x is 0, then we're trying to divide by 0 and we got problems. So right away, the domain cannot include 0. Now, the other thing is we need this piece. We need the radicand down there, 2 minus x squared. We need that to be positive, strictly positive. So we get this, and we can solve this for x, or at least absolute value of x, just like we did a moment ago. So basically add x squared, and then you get x squared is less than 2. So then when you take the square root, you're going to get absolute value of x is less than or equal to root 2. Or sorry, not less than or equal to, but just less than root 2. But then we got to remember that x cannot be 0. So we do have a little bit of a gap there. Looks kind of like a smiley face, right? So we do have a bit of a gap there. So it's from negative root 2 to 0, skip 0, and then 0 to root 2. Right, there we go. Okay, now let's get the next result. So here's the next result. The derivative of arc cosine of x is negative 1 over square root of 1 minus x squared. So it's very, very similar to the derivative of arc sine. In fact, it is the same, except it's negative. It's the same, except it's negative, right? Let's go back to, where is it? This one right here. So yeah, here's arc sine. Here's arc cosine. So we're not going to do this proof, but I recommend you try it yourself. So try this one yourself. Use implicit differentiation. The technique is identical to, or almost identical to, what we did in the previous proof. It's a good exercise. Try to work it out on your own. But the one we're going to prove next is this one. So what is the derivative of arctangent? The derivative of arctangent is 1 over 1 plus x squared. 1 over 1 plus x squared. And here's the proof. So just like before, we're going to give a name to our inverse function. We're going to let y be arctangent of x. And that means that tangent of y equals x by definition. So again, it's the same technique. Give your inverse a name, so that way you can switch the inputs and the outputs, and then get back into the realm of the original function, not the inverse function. Same technique as before, differentiate with respect to x. The derivative of tangent is secant squared, inside left alone, times derivative of the inside, which will be dy dx, or y prime. D dx of x is 1, and then when we solve for dy dx, we get this. So 1 over secant squared y. Now, here's the here's the fun part. Secant squared y, well, we have a trig identity for that. We got a trig identity for that, right? Secant squared y is 1 plus tan squared y. That's one of the 6 that you're supposed to have memorized. The tanning identity, right? That's the tanning identity. Well, what is tangent of y? It's x. So this one falls out even more quickly. You just get it right there. And that's the proof. All right. Okay. So now that we have these three, we've got the derivative of arcsine, arccosine, and arctangent. There are equivalent integral results. So let's take a look at those at a glance. So when you combine the 3 theorems that we just proved, or at least stated and proved 2 of them, we get this. The integral of this is equal to arcsine of x plus c. The integral of this is equal to arccosine x plus c. And the integral of this is equal to arctan of x plus c, right? So some of you might be wondering at this moment, like, how much of these things do I need to memorize? Well, these 3 you should definitely memorize. And when I say these 3, I mean the derivatives and these integrals. But also, if you have one of them memorized, one set memorized, you've got the other set memorized for free. We're going to see these structures a lot when we get into chapter 7, and how you compute these integrals is specifically getting them written as arcsine and arccosine and arctangent. So what I'm saying is that this is a structure that you want to be able to recognize. You want to be able to recognize that structure. Same with this one, and same with this one. And you want to be able to remember that this thing is the derivative of arcsine. And because this thing is the derivative of arcsine, the integral of this thing has to be arcsine. There you go. That's what you're getting right there. Because when you integrate the derivative, you get the original function back. All right, so you do need to memorize those. Commit those to memory. You can use flashcards. You can just write them up on your, like the mirror in your bathroom or something just to remind you what these are, because we will see them a lot later. And now we're going to use them right now. So with that in mind, see if you can compute this integral on your own, and then we'll do it together. So think about what you would do first. All right, now say something out loud to yourself about how you would proceed. All right, now try to work it out on your own. It is a definite integral, so your final answer should be a number. See what you get. All right, now let's do it together. So the first thing that I notice here is this structure looks pretty familiar. It looks very much like it could be arcsine of x, or I should say the derivative of arcsine of x, right? Because you've got that 1 over square root of 1 minus something. So if this could be written as something squared, then it would literally be the derivative of arcsine. So I think the first thing we're going to have to do is a u substitution, or use the substitution rule. So here I'm going to rewrite 4x squared as 2x squared. Let u be equal to 2x. So we're going to change the variable of integration. So when u is equal to 2x, du is equal to 2 dx. And remember this, and I said this in the reviews, and I will say this a lot during the class, when you have a definite integral, you must change the bounds after you do a change of variables. Keep that in mind. These bounds are in terms of x. They are not in terms of u. So if you change the variable of integration to be something else, then you also need to change the bounds so that they are in terms of that other variable. So when x is equal to 0, u is also equal to 0. And when x is equal to 1/4, u is equal to 1/2. Using just this relationship, that's the connection between u and x. Thus, our integral becomes this one. So when we switch our variable of integration to be u, we get that, and then voila, look at that structure. 1 over square root of 1 minus u squared, that's the derivative of arcsine. That's the derivative of arcsine. So if we integrate the derivative of arcsine, we get arcsine. And now here's the other thing, another reason why you should change the bounds. Since you've already changed the bounds, there's no need to back substitute. Remember, these bounds are in terms of u. So I just need to evaluate sine inverse of u at these bounds. That's it. I don't need to plug in 2x. I don't need to go backward and change anything. We've already changed it. We're just marching forward. So we get sine inverse of 1/2 minus sine inverse of 0. Sine inverse of 1/2 is pi over 6. That's the angle whose sine is 1/2. Sine inverse of 0 is the angle whose sine is 0. That's 0. So then we get pi over 12 in the end. All right. Okay. So now here is a summary of the derivative formulas. So the ones that you need to memorize are the 3 that I already said. So these 3, here we go, these 3 you must have memorized. Okay, you must memorize these. But here's the complete table. We're not going to go through these proofs. If you'd like to see the proofs, I do believe the book has all those proofs in there. The proofs are similar. You could actually do these yourself. It's just the same technique. Label your inverse function, rewrite it in terms of its original function, use implicit differentiation, and then algebra. All right? So this is the summary. These are all the derivatives. Notice here we've got the derivative of arc cosecant, the derivative of arc secant, and the derivative of arc cotangent. All right, but yes, memorize these ones. Like I say down here, you must have those ones memorized. All right? Okay, now on that note, let's play. So that's it. I'll try not to ramble on too much more, but we will work on these in the activity. You've got those few derivative formulas that you have to have memorized and the corresponding integral formulas. The next section is a little bit of a departure in some sense. The next section is all about hyperbolic functions. And so we'll talk about those next time. So for now, I will bid you farewell, and I will see you next time. Thanks for listening.